Hello everyone, today we will be solving one more numerical on Smith chart. So the question is a 30 meter long lossless transmission line with Z not equal to 50 ohm, that's a characteristic impedance, operating at 2 megahertz is terminated with the load ZL equal to 60 plus J40 ohm. If U is equals to 0.6 C on the line, what is that U? That is the speed. Find reflection coefficient, standing wave ratio, input impedance, and one more question is at what distance is V max from the load. Okay. So first what you have to find, always we have to normalize this particular ZL so that we can point it on the Smith chart. So ZL equal to 60 plus G40. What I'll do, I'll take small ZL equal to 60 plus G40 divided by 50. Okay, so I'll just do that. 60 plus 40I divided by 50. So what I'm getting the value around 1.2 plus 0.8 G. Okay, now I have to note this thing in the Smith chart. So where is that? 1.2 is here. As you see, I'll go from here, from the real axis, and then where is 0.8? 0.8 is here. So I'll come here, 0.8 and 1.2. So let me check again, 0.8 and 1.2. So this is the point of impedance. So ZL equal to 1.2 plus 0.8 J. Okay, so now what you have to do, first thing you have to find the reflection coefficient. What I'll do, first we have to find reflection coefficient. So what I'll do, there are two methods. Okay, in the last video what we have learned was to draw the circle, and then from somewhere from the circle point you have to draw a straight line. Yes, that works well. One more what I'll do, let me show. So from the center I'm drawing a straight line. See, this is the center. From there I'm drawing a straight line till here. Okay, see, now let me note down the values. Let me write this as some O, P, Q. How do you measure the reflection coefficient? See, that will be OP divided by OQ. Okay, so how much I'm getting OP? OP I'm getting somewhere around 2.6. OQ I'm getting it around 7.8. Okay, from here to this particular center point. Okay, so now let's calculate how much do I get. 2.6 divided by 7.8, and I'm getting it around 0.33. So I'll write 0.33, and angle we have found 56 degree. The question is reflection coefficient done, standing wave ratio done, the input impedance. So to write the input impedance, you should know for what distance you should travel, right? So how exactly you get that? See, they have given the length of transmission line in terms of meter, but usually we write it in terms of wavelength. So for that, first let us find wavelength using this particular data. So U equal to 0.6 C they have given. Lambda is equals to, usually it is C by F for any microwave line, but here it is 0.6 C by F. F is given 2 into 10 to the power 6. C is your regular 3 into 10 to the power 8. Okay, so let's find, divide by, let's do that, 6. So I'm getting the value of lambda as 90. Okay, so we got lambda as 90 meter. So what is the length of your transmission line in terms of lambda? So that will be 30 divided by 90 lambda, so that will be given by 0.333. So I'll just keep it to 0.33 lambda. Okay, so now you have to find input impedance. So already, where is this particular load impedance? Load impedance is somewhere at, I need to calculate from the load side, right? Somewhere at, you see, from here I will calculate, and I'm moving towards the generator, somewhere here 0.174. Okay, 0.174 is where your load at, 0.174 lambda, plus now what I have to do, I have to move from here 0.33 lambda to obtain input impedance. How much I'll get? Let me calculate. Okay, 0.174 plus 0.33. Oh, it is coming 0.504. But you should be knowing the overall length of this whole Smith chart is around 0.5 lambda. Not around, it is exactly 0.5 lambda. So from here to here, if you calculate, that will be 0.25. From here to here, 0.25. But the value we have got is above 0.5. So what we will do? We will just subtract it from 0.5, or you subtract 0.5 from it. So 0.004 lambda. Correct? So now how will I get the input impedance? From this particular point, you see, from this particular point, I have to move towards the generator, right? So where is 0.004? I see 0.04 here. So maybe this is 0.03, this is 0.02, and this is 0.01. If that is 0.01, this might be 0.004. So now let us draw a straight line from the center. Center is here. From the center to this point. Okay, how do you find input impedance? See this particular point where the VSWR circle is intersecting with the straight line, that will be your input impedance. So how much is the input impedance I have to find? So what is the value? If I just take it here, it is somewhere 0.49. Let me find out here. This is 0.1. So maybe this is 0.05. And this will be 0.025 or 0.03, I guess. So I will write down input impedance I am getting as 0.49 plus J 0.025. Don't forget, you have to multiply by characteristic impedance. So I will write it as 0.49 into 0.49 plus 0.025i into 15. Value you see 24.5 plus 1.25 J ohm. This is the input impedance I am getting. Okay. So now till C we are done. Next question is, at what distance is Vmax from the load? Where do you find Vmax? Remember, always Vmax here, V minimum here. Now we are worried about the load. So from here to here, what is the distance I have to calculate? Easy way. What you can do is 0.25. This is 0.25. What we had earlier was here 0.174. Okay. So for this particular question, it is at a distance of 0.25 lambda minus 0.174 lambda, that is equals to 0.076 lambda, or if you want to write it in meter, what you can do? Multiply this with 90, that is your lambda value, right? So it is somewhere around 6.84 meter from the load. So that's how you solve the problem, and this is how your Smith chart is looking like. If you want to verify your reflection coefficient, what you can do? just draw the straight line from here to this particular measurement meter, and then you get the value. Otherwise, one more method, ZL minus Z naught divided by ZL plus Z naught. So, thank you.